Hey everyone, we're taking a look at Notebook 17. So you might want to pause the video and go ahead into D2L and get Notebook 17 open. Why? We're going to be talking about the Chi-Squared GOF or goodness of fit test. So let me get rid of those lines and let's jump into Notebook 17. So you can see that I'm in Notebook 17 analyzing one category variable. And these are the words I'm saying, goodness of fit. Again, this is the lowercase Greek letter chi. So chi-square is the test that we're running. And again, we usually abbreviate this as GOF, chi-square GOF, rather than writing out the longer goodness of fit. So what are we doing? We're testing a probability model. Okay. We are going to test a probability model, and the first one's rather interesting. So we're doing hypothesis testing, and they give us example one. Joe and Mo are arguing about how often the bus is late. And notice that Joe has the null hypothesis, right? That's going to be our H sub 0, is that the bus is late 70% of the time. Okay. And then we have Mo, who says the bus is late more than 70% of the time. And as we move down, we realize there's another friend, Poe, who said it's late less than 70. So we have more than 70 and we have less than 70. And believe it or not, there's one more friend, Bo, who who doesn't know whether it's more or less than 70, but just denies it's 70. So real quickly, let's jump back into our notes, and let me just show you. All right, so chi-squared goodness of fit, what is it supposed to do? It's supposed to see how well the observed data conform to some probabilities. Okay, for example, with dice rolls, we would expect each of the numbers to land face up 1/6 of the time. But what if we see this observed data? So Ariel can use this question and set up the probability model based on the probabilities of 1/6 and see this observed data based on her 200 times that she rolled the die, and she can determine scientifically whether or not the die are fair. Okay, so that's basically what we're using the chi-squared goodness of fit test to do, to test some probability model. And in the first three examples in our lecture notebook, we've got these three alternatives. So Mo thinks it's less than, that's the alternative, excuse me, greater than 70%. Poe thinks it's less than 70%. And Bo's not sure greater or less than, but is pretty sure it's different. Now notice that we have observed data from 200 trials, and the bus was late 150 times, which was 75% of the time. Okay, so let's go back in. Sorry. Let's go back into the notebook. And the first thing they do is we're examining example one with a simulation. Okay, so the first thing we do is we just make an array that's 70% late and 30% on time. Okay, and then we create this function, distance under null, which tells us how far our simulated proportion is from 70%. And there's an example down here to say how to transform these from proportions into percents or counts. Okay, and then we're running this for loop 1,000 times, and we're seeing what happens. So let me make sure that I've executed these code blocks so that they will run, and let me make sure that that asterisk is gone because it's run 10,000 times. And there we go. There's a histogram of the distribution. And notice that it's approximately centered on 0. Okay. And And then the question is, well, we haven't really looked at what happened with this observed statistic, right? The observation was that the bus appeared about 75% of the time to be late. And so the difference between that and the 70% is about 5%, about a 0.05. But the question is, where does the 0.05 land in the histogram? That'll help us determine the p-value. What's the p-value? The p-value is the probability that the null is true. Okay, so we've got this, and they calculate the empirical p. Okay, that's good. And then they're going to, after we have this empirical p, they're going to shade the part of the bell curve that's related to it. Okay. So, interpreting the p-value, we have the chance that the bus is late 70% of the time. And we get a statistic that is 0.05 or greater. And it actually happens that the chance of this happening is 6.6%. So the chance of the bus being late more than 70% of the time is 6.6%. That's the amount of area of this histogram that is shaded. That's what we're showing. And the problem is that with an alpha of 5%, with an alpha of 0.05, our p-value is greater, so we fail to reject the null, okay? And we find that the bus is not likely to be late greater than 70% of the time. Okay, so that's doing it with the just doing the probabilities ourselves. So we actually calculated all of those probabilities, ran it through 10,000 times. Oh, wow, check this out. We can calculate the p-value directly with just one line of code. And please notice that this is the binom test. Now, we said we were going to talk about goodness of fit, and I'll explain why we're using the binomial test in just a second. But here we go. We've got the greater than, and they're changing the data. Why? Well, what if the bus was late 155 out of 200 times instead of 150? So they're changing it slightly. Okay. And notice that this p-value would be a reject the null p-value, right? This p-value is in fact less than 0.05, unlike the previous one. So here we would reject the null with the new data, right? That's new data. The 155 out of 200 times the bus was late. The original data was 150. Okay, so if we change the data, we notice that the p-values are going to change. And they go through this really interesting table of the number of times the bus is late and the p-value empirically and theoretically. All of this code up here does that. Okay, and it shows us that that you can see the change right about here, where all of these up here, when the bus is late 152 times or more, we have p-values that are small enough up here to reject the null. But down here, they're going to be greater than 0.05, and we're going to fail to reject the null. So you're starting to see the evidence levels that will, in fact, help us reject the null. Okay. Sorry, let me... So the binomial test, they actually give this probability formula that it uses. And, okay, and then we sum all these things up. This shows this current example mathematically what we do. All right. So why did we use the binomial test? Well, it turns out that the chi-squared procedures require 3 or more levels of the category variable. So in other words, we need a probability model with at least 3 different probabilities in it. So the example I gave about the dice rolls, well, the dice has 6 different sides. So there are 6 different probabilities in that model. Now they all happen to be 1/6. They're the same value. But we can't use it when there are only 2, like a coin flip, heads or tails. If there's only success or failure, and that's what we had in the bus example, right? We just had this percentage of the time late, and 100% minus that percentage on time. Okay, so why? Well, we end up using the binomial test for more accurate p-values because the chi-squared wasn't really made to use in this situation. Can we use it in this situation? It'll run, but it's going to be much more accurate if we use the binomial test. Okay, and please notice that this isn't really hard to run. For the binomial test is just binom underscore test, and then we put the number of successes, comma, the total number of trials, and then the chance of success. And the thing runs. Okay? And the next thing they do is they change the bus weight example. Why? Well, so we can use a chi-squared goodness of fit. And notice now that there are 3 different probabilities in this model. So chi-squared is appropriate. And our null hypothesis in a chi-squared goodness of fit is basically the probability model, right? So the probability model here is that the bus is going to be a little bit late 50% of the time, and it's going to be very late 20% of the time, and it's going to be on time about 30% of the time. And the alternative is that the null model is wrong, okay? Well, let's see what happens. All right, if we get past this, I'm sorry. We're failing to reject the null on all of these tests. I didn't mention that. That p-value is much, much greater than 0.05. Also in example 3, with the not equal to, we still have a p-value that was greater than 0.05. So all 3 of the tests run with the original data fail to reject the null. And so we don't have any evidence that the bus is late more often than 70% or less often than 70%. Right now, about 70% is about our best guess. Okay, so now what goes on is we have the new test, and we're gonna do the same thing. We're gonna get 200 trials. We're gonna note the arrival in 3 categories. Okay, and suppose that the observed data is that the bus is only a little bit late 90 times, very late 55 times, and on time 55 times. Okay, well, that would be interesting. All right, so now we're talking about the chi-squared. Again, we're in an appropriate situation for the chi-squared goodness of fit test. And when you see this, that's what we're saying. When we say chi-squared, that's it. That's the symbol we're referring to. And notice how this is run, okay? So first of all, we need an array. And actually, it turns out we need a matrix in the next video. And we're comparing these outcomes to what? To 50%, 20%, and 30%. That was our model. Why are we multiplying by 200? That's the number of days that they counted on the bus, right? That's their sample size. So we're taking our sample size. We have the probability model right here times the sample size. Okay? And then what are we putting into this function? Okay? We are putting the observed data in as an array, right? That's the observed data right there. And then in the same order, notice, we're putting the probabilities times The sample size. Why? Well, we don't want the probabilities. We want the number of times you'd expect to see the bus show up on time. For example, if it shows up, a little bit late 50% of the time, you multiply that by 200, you get, well, about 100 of these should have been in that category. It turns out that instead of 100, we have a value of 90. So we can see that the observed data isn't exactly matching the probability model. Okay, so what does the second thing do? That's the counts we would expect. The expected counts based on the probability model. Okay, so I do observed, comma, expected. They're just two arrays. And I get a p-value that is less than alpha, right? We get a p-value that is less than 0.05, and therefore, in this case, we're going to reject the null. And notice that, again, they're doing this. We were expecting the bus to be very late 45% of the time, and the 55 over 200, 27.5. So you can compare those values of 0.5 to 0.45, and the 0.2 and 0.3 came out to be 0.275. So we reject the null. The probability model doesn't quite seem right. And the reporting out says exactly that. And it turns out that it's a lot late more often than predicted. And it's on time less often than predicted. Okay, how do we find this out? Does the statistical test tell us this fact? No. No. That's why we did this work up above, right, with the actual counts and figuring out, what these percentages were. Why did we do that? Well, we rejected the null and found out the probability model is wrong, but that doesn't help us figure out what's actually going on. Is it a little bit late, a lot late? And it turns out that it's far too often it's a lot late, and it's not on time enough. So this one's okay, but these two were a mess. And anyway, all three of them turned out to be wrong. Together, the model was in fact incorrect. Okay. And then this talks about the reason why we use z-test for population proportion. And and notice that, yes, you can use the chi-squared. In the earlier example, notice that the p-values are slightly different. So in other words, when we use the chi-squared test, and there's only two options, right? So here there was the 70% on time, 70% late, and the 30% on time in the model. And when we run it as a chi-square, right, it turns out that we get a slightly different p-value than we did the other way. And there is the formula for chi-squared, how you actually calculate it. And these are this means the observed data compared to what we'd expect based on the probability model. And so these are cells in our arrays that are getting compared to each other in the chi-squared test. You don't have to know that formula, but you will see that a lot in statistics. So here we go. Here's a summary of exactly what we found. We started with our null hypothesis being this probability model. The alternative is that the model is wrong. And we made an array of the observed data, right? So the observed array is just the data that they found when watching the bus 200 times. And then the null counts, right, are what are the values that they would expect to go in here. if there were 200 trials and these probabilities were in fact correct. So we just take the probabilities and multiply each one by the sample size to get the expected number of times you would expect, the expected number of times that the bus is a little bit late or very late or on time. And again, I just want to point out that we put the observed array in first and the null count array in second. So we have observed and we have expected. And they go in that order. So this is for chi-squared goodness of fit, right? We have observed. All I have to do is put in two arrays, the observed array and the null count array. All right. Now the final example in this notebook goes over Benford's law. And Benford's law is kind of little known, but it turns out to be correct a large proportion of the time. And they say, look, in a large numeric data set, most of the first digits, the leading digits, are small. You know, your ones and twos and threes. And then a lot fewer are large, like 7, 8s, and 9s. You're like, what? What in the world is this? Well, so what we do is we grab the population in the U.S. counties, right? And there are something over 3,000 U.S. counties, right? So we're going to look at the counties in the U.S. and see whether or not they follow Benford's law. And he gives us a probability formula, so our null hypothesis, our null and alternative, we'll be able to set up. The null is that the data conform to Benford's law, and the alternative is that the data do not conform to Benford's law. Okay? So the code that we're going to be using, this is the calculation of the Benford prediction, that we're using the logarithm of 1 over 1 divided by the digits times the number of counties. Why are we doing this? Again, this is our sample size. So we're multiplying by the sample size. Okay. And then we're going to have the actual statistics, right? The counts are going to go in first. Why? That's our observed data. And then our predicted, what's expected based on our prediction, that's going to be in an array called Benford underscore prediction. So let's take a look at that. Oh, and I'm sorry, the thing that the notebook does is it goes over the different chi-squared distributions, and you can see them. It is not bell-shaped. It does have a hump, and as the degrees of freedom gets larger, right? The blue one is 5, the red one is 10, and the yellow one is orange. So as the degrees of freedom get bigger, the peak is less high and it travels down the x-axis. Okay, and then this is an animation, and you can see the degrees of freedom are increasing and the peak or the bump is getting smaller, less tall, and traveling to the right. So as the degrees of freedom get larger, that bump moves to the right. So that is the chi-squared distribution. That is the mathematical graph that we're using in this case. And so they actually show the, they actually are showing the p-value is the area in red there, the part of underneath the curve that we shade. And in the chi-squared, there's no less than or greater than. We only shade to the right, and the more that we shade, the more likely it is that the data do fit the probability model. When there's very little shaded area, percentage-wise under the curve, then we reject the null. Okay, so now we get down into Benford's law, and I said that Benford was a probability model, had a probability model, and I sort of glossed over that. But this is the prediction, that the base 10 logarithm of 1 plus 1 over k should give us the probability that the digit k should occur. Okay, so what does that mean? It's an ugly formula, no doubt. You don't have to remember it. That's Benford's law. And the computer is going to do the work for us. Okay, so first thing is, it turns out that we have a table, counties.csv, which has all of the counties in the United States. And notice that there are 3,142 rows in this table. So yeah, something over 3,000 counties in the country. And now we're arranging things so that we can figure out the first digits. So notice that we have the population. The first digit here is a 5. The first digit here is a 1. The first digit here is a 2. Okay, so we've got to figure this out. And so what they're doing is we're showing the Benford law probabilities. Notice, just like we said, that it's much more likely that the leading digit in this data set of numbers in this data set will be small. And there's a much smaller probability that we'll have a large number, like a 7, 8, or a 9, show up as the leading digits. So this is kind of nice to explain Benford's law. It's sort of a confusing thing, but it turns out that in these big numeric data sets, this is almost always true, that the small numbers are the ones that are much more likely to be leading digits. Okay, so we've got the model, and and it says you don't have to understand how this function works. Basically, it's going in there and it's getting the first digit, right? And now it's doing the first digits for all of the counties, and it's applying it to the column population again. So we don't care about the first digit of the county. It doesn't have any digits. We're making sure that we get the first digit. And when you run this array, now we've got a table that tells us the county, the population, and the first digit of that population. And like we said, there are 3,142 counties. And then this is kind of cool. We have a bar graph that shows the Benford law prediction in blue. Excuse me. The Benford law prediction is in yellow, and the actual proportion is in blue. And by the way, notice that the two graphs, while they aren't identical, they are very, very similar. Okay, so now we're importing scipy.stats. Why? So we can run this, and it's the same way that we ran it before, right? We have the observed data going in first. We have the data that we predict based on the probability model that goes in second. So observed first and expected second. And when we run it, and by the way, that's the part you need to know. This last line is what we will do and do on the project. Are you going to have to do the Benford's law calculations? No. Okay, so run it. And let me, I'm trying to show both of these. I'm not going to be able to. Just notice that the p-value is 0.4, which is greater than 0.05, which is our alpha. So we are going to fail to reject the null, right? So fail, sorry, my my handwriting with the mouse is not perfect by any stretch, but we are going to fail to reject the null, which means what? Well, rejecting the null would have meant that the probability model is wrong. Okay? But here we fail to reject the null. Why? Well, it appears that even though there's a little bit of difference in the proportions we expected, the percent of the time we expected things to happen, the gaps are just not that big. And here's one of the bigger gaps for the 5s. But notice the 4s and the 6s are almost spot on. The 7s are almost spot on. So yeah, there are some tiny little differences and a little bit bigger differences. But overall, the model actually does predict the number of leading digits, or the percentage of times we'll see each of these leading digits. So we fail to reject the null, and the probability model appeared to be okay. And notice, like I said, that when we have a large percent of the area under the curve shaded, right, that's when we fail to reject the null. Why? Well, if we're going to reject the null, the shaded area would have to be less than 5%. Less than an alpha equals 0.05 in this case. And this is clearly not. This is 40%, right? We're seeing 40% of the area under the curve is shaded. Why do I know that? That's from the p-value up above. And so that's what it looks like visually when we fail to reject the null. And then we have evidence that the populations, that the first digits of the populations do conform to Benford's law. Okay. And again, they have reported the chi-squared test statistic and the p-value. Okay. And we have this figure again. And we're going back to the one sample z-test for proportions. And let me jump in here. So we've got two tests that are doing the same thing. And it turns out that we use a z-test for population proportion. And I showed you earlier that we're using the binomial test. And then the question is, why two different tests? Okay, so what do we use them for? Remember that the chi-squared statistic is going to be really accurate as long as I have 3 or more probabilities in my model. If I only have 2, then I need to use one of these. These are more appropriate, and they're going to have more accurate p-values. Is this the world's biggest deal? No, it's not. And it turns out that the binomial test happens to be a test that requires a huge amount of computer power, and the z-test requires much less. So it turns out that we have 2, and we use the binomial test when the sample size is small. But if the sample size is large, then the binomial test is just requires too much computer power. You end up needing a supercomputer to run it. So we run the z-test for large samples. Okay, so small samples, we'll run the binomial test. And for large samples, we will run the z-test for population proportion. And in the middle, they largely agree. Not exactly, but they're much better than using the chi-squared. Remember, chi-squared should only be used when there are 3 or more probabilities in the comparison. Okay, so the notebook basically explains what I just did. And then what's interesting is the notebook actually has a z proportion test written out. This is something that is given right here. In this code block, this will run a z proportion test if you need it to. This is just something to remember that, Notebook 17 has this. And they just run through it real quickly and show the z proportion test. Well, we did these with the binomial test earlier. So you can compare the p-values, right? So the p-value of 0.06954 compared to a p-value of 0.0614. Okay, are they identical? No. But they're a lot closer. The z-test, the z-test and the binomial test the p-values will be a lot more accurate than the chi-squared. And that's what these blocks are showing. And again, you see the z proportion test gives us 0.1222 compared to the binomial test giving us a 0.1423. And they talk about this continuity correction, which does make the z-test slightly more accurate. Okay, but in the grand scheme of things, what do we need to know? this is about the chi-squared test, so let me jump back up to where we actually had a chi-squared test, right? When do we use the chi-squared? We use it when we have 3 or more probabilities in our model. And how do we make it work? We put in 2 arrays. The first array we put in is the observed array, and the second array we put in is what we would expected based on the number of the sample size. So we multiply the sample size by all of the probabilities. Okay, and that's how you use chi-squared goodness of fit.